recording. Hello. All right, let's begin, everyone. This is the lecture summary for today. And I have added the annotation to the handwritten notes so that you can search also easily. And we still have the lecture summary sheet of Team 6 and Team 8. So can you pick that up? Okay, so I'd like to continue to discuss, give you the solution guide for problem 4.7. And this is related to the creation of the table or spreadsheet that would allow you to detect the musical notes based on the frequency, right, as detected from fast Fourier transform. Okay, so let me bring up section 25E that you saw last time. Okay, this is section 25E here, and on the that was on the left. On the right, let me go down. Okay, and I started from this page. Okay, now let me simply step back and motivate, because we have more time, so I'd like to motivate a little before we started. So this is the recording of sound, actually a beautiful piano classical music piece. We'll come back to that later, but I just want to have a quick motivation. So, and below what you see here is the fast Fourier transform spectrum. Okay, and the horizontal line is frequency in hertz, and vertical line is in decibel. We'll get to that later. Essentially, it measures how strong the signal would be. Okay, that's for each frequency. So the goal is, say for example, at each peak here, that's when the sound is loudest. You want to find out which note corresponds to a peak, right, on the FFT spectrum. And that is, for example, here, you see, for example, the highest peak at minus 18 decibel. And like I said, I'll explain that later in the future. But you see the highest peak corresponds to the note C4. Okay, that's the middle C on the piano keyboard. C4 plays a very important role. And the note C4, the frequency is 262 hertz, okay, as shown there. So that's the goal. Okay. Now, a more realistic case is shown down here. Let's see, right here. Okay, where you do not have exactly, the frequency is given here in the first column, and you need to detect the closest key or note that would be closest to a given frequency. Now, if the frequency is exactly on the note, then this number here would be an integer. That's the number of keys from the note A0. Okay, I could remind you that on a piano keyboard, I'll have another slide where I would show the whole piano keyboard for you. But right now, just take my words that A0 would be the leftmost key. Okay, and this column here represents the number of keys or semitones from A0. And if this number is not exactly an integer, that means that you know, the piano string or the guitar string would be mistuned. Okay, exactly tuned, then this number would be exactly an integer. Okay, so let me bring up section 25C. So to show you, so that was E, C, I think, yeah, okay. Right, so this gives you some idea. Yeah, so a piano, typical piano in modern days has 88 keys, okay? With the leftmost key is the lowest frequency, and that, let me zoom in, and that is the key A0, note A0 at 27.5 Hertz, okay? And now you see A1 is 12 semitones, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you know, so you can count 12. And so A1 is 1 octave above A0. And so what is 1 octave? 1 octave is when you double the frequency. Okay, so the note A1 has a frequency that is exactly 2 times 27.5 Hertz. Okay, so you keep multiply by 2. And there's a history about that, and there's an engineering and physics explanation of why the octave is by doubling or multiply by 2 the frequencies. Okay. But right now, my focus is to show to you how to create that spreadsheet for music note detection. All right. So I just want to introduce a few keywords so that the explanation would be clear, right? So you have A1, and then you have here, I denote A5. Here C4 is a very important key, and the way to recognize it is, you know, you can look at the 3 white keys with 2 black keys in the middle, and so the one on the left is the C key. All right, and A is just you see right here, A, B, C. So this is the A key, very similar to the A key here, right? A1, A, B, C. So this is the C C key, and this is C1, right? Now, and A4, you recall that this note, A4, also called A440, that is tuned exactly to 440 Hertz, and that's the pitch standard that all concert and all modern instrument is tuned after this frequency 440. And on a piano, it's key number 49, okay, as you saw last time. So here you see the whole piano keyboard, and the highest key is key C, the note C8, and that's key number 88, right? There are 88 keys. So it goes from A0 to C8. And this is called the scientific music notation. Right? The first letter from A to G denotes the note name within an octave, and the number is the octave number. Okay. Now, now, for some reason, the beginning of an octave is the C note. So you see here, this is C1, and before before the note C1 is the octave 0. That's why this key here is the leftmost key, or key number 1 on the piano keyboard is A0, and then you have B0, and then you have C1, right? And then you have D1, E1, until you have here is C2. This is key or note C2, whereas A1 is over here, so A, B, C. This is C2, C3, and C4. This is called the middle C, a very important key on the piano. And then you have this is A4, right? So an octave always starts with a C note, for whatever reason. That's how it is. I'm sure there's an explanation, but I'd like to focus on the construction of the spreadsheet. Okay, and in this figure here, let me the octave is also denoted here. You see, for example, the second octave, this key here is a key C2. Okay, so then this image here is very good in showing you the division in octave, right? And within an octave, you have 12 semitones. Okay, so with that background in mind, let me zoom out also here. You have here the real piano with note or key from A0 to C8 with the middle C, C4. Okay, and these we will come back when we talk about the Beatles. All right, so that gives you a pictorial idea of why we do this table, right? This is called the 12-tone equal temperament, and the goal of problem 4.7 is to set up your spreadsheet in preparation for note detection, music note detection. And what I give you here is my own spreadsheet that you can use to compare with your spreadsheet, okay, as a partial answer if you like. And I give you the formula for all columns except one, and that's a very easy one. So let me bring up the middle window to zoom in again. So one more time, this is the real world. This is the real case here, where the frequency would not fall in principle exactly on the key, on the piano key or on the note, and usually you have some mistuning. Okay, now let's do the ideal case, and that's the spreadsheet that you are preparing as shown before to you, and now I hope that you get a little clearer. And for a quick review, this is an important formula that provides you with the frequency, right? So given a key number on the piano, it will give you, this formula give you the frequency for that key number. So for example, so here F1 is the frequency of key number 1, and key number 1 corresponds to note A0, and that's at 27.5 Hertz, and you can put the number at F1 multiplied by 2 to the power 1 over 12, and then raised to the power n minus 1 as mentioned last time. And last time I also mentioned to you this example. If you put n equal to 49 into this formula here, n equal to 49, then you recover exactly the frequency of key number 49 equal to 440 Hertz, and that corresponds to note A4 or A440. That's a pitch standard. Whereas key number 40, corresponds to the middle C or the note C4, and the frequency is 261 Hertz or 262 Hertz. Okay, just by using that formula. But for music note detection, so we want to use the the inverse. Okay, so I already mentioned to you that by just taking the logarithm, then you can obtain this formula, right? That formula would give you, so given a frequency, you can find the key or number of semitone, okay, corresponding to that frequency. All right, or n-1 is the number of semitone from key A0, the first key on the piano. Okay, so we went through this last time, and so let me bring up, yeah, so this way you can see both. Okay, so the frequency is given here, the number of keys from A0 or n-1, that's this formula, and the octave key number, that means the key number within one octave is given by this formula here. Okay, I found this formula by playing around, and I have already explained the meaning of the function. Round is to round up, right? n-1, n-1 is the result of using the formula above here, and to zero decimal digit, and then the modulo function is to take this called m, this integer, divide by 12 and find the remainder. So the remainder is obtained by the modulo function and add 1 to the result. And so that would give you the octave key number. Okay. Now from the octave key number, so all of these formulas I gave you, the only formula that I didn't give you is this column here, and that is very simple. And let me explain how to obtain it. It's just if then else. Okay, so let me go over here, and yeah, maybe let me show you. So this is a portion of the spreadsheet that goes from key number 73 to 88. So when you create your spreadsheet, you can use this to check, right? And so here, all you need is just to write if then else. If the octave key number is 1, then the note name is A. If the octave key number is 2, then you give A sharp, right? Give name A sharp, and so on and so forth. So if for octave key number 3, that's B. For octave key number 4, that's C, and so on and so forth. So this is already the answer. So you just use these correspondence between the octave key number and the note name to code out. That's all. It's just if then else, if then else. That's all. Okay, and that's the only formula that you need to create. All right. Now the octave number, I give it to you, and that's right here. And it looks a little more complex than the other formula, because in this formula itself it contains an if then else structure. Okay, the reason is what I explained to you. There may be a historical reason why the octave always starts with a C note. So that's why you see all the notes before this C note has the octave number less than this octave number by 1, right? So here this is octave number 6. You have A sharp, and B, and then you have C7, right? So this is B6, whereas this note here is B7. C7. So again, the octave always starts with the C note, all right? And because of this, that I have to have an if then else structure, right? So if the number here, if the octave key number is less than 4, then the octave number would be less than from C on. So Then you see, if the key number in an octave is less than 4, then I take the quotient of the rounded up number of n minus 1 with 0 digit divided by 12. But I take the quotient, not the remainder. The remainder is with the modulo function, right? And if the key number in an octave, see, key number in an octave is greater than or equal to 4, that means from 4 to 12, then I take the same quotient like up there, but I add 1, right? So because if you take the quotient, you would only have 6, for example, in this case, and then I add 1, so that when you go to the C note, it would become C7, right? Instead of C6, just because of the numbering of the octave by convention or by whatever reason. There's a history behind that. Okay, that's it. So this is the formula. So you have all of the formula, including this one. So I will explain this one. Okay, the first column. The first column is already, in a way, implicit in the formula for the 12-tone equal temperament. So before moving that, let me perhaps go over here, okay, and scroll down. So to the same place here, and zoom in, right, this formula here. Essentially, basically these are just by multiplying the same number over and over, and that's 2 to the power 1 over 12, okay? And so you start with, let me go over here and go back to the top of the table. And the top of the table, start with key number 1 on the piano keyboard, and let me put the mask. You see the first, for the first note, A0, the frequency factor is 1, right? And then for the next note, you multiply by 2 to the power 1 over 12. And that's exactly 1.059 dot dot dot. Okay? So this number here is 2 to the power 1 over 12. So that is the frequency factor. When you take 27.5 and multiply with this frequency factor, you obtain this one, 29.1. That's the frequency for the A sharp note. Okay? And then for the third row, it's the same thing. You multiply by 2 to the power 1 over 12 again. So therefore, this number here is 2 to the power 1 over 12 squared, right? Or 2 to the power 2 over 12. All right? That's this number. And then you take 27.5 multiplied by this factor, then you get the frequency, which is 30.87, and that corresponds to note B0. Okay? And then so on and so forth. If you multiply or raise to the power 12, you know, when you are at row 12 here, right, this yeah, actually this is to row 2, you have number 1, right? And so therefore row 13, that would be 2 to the 1 over 12 to the power 12. Okay, that's exactly equal to 2. All right. Okay, so that's 2 times, right? Because when you take the frequency 27.5 multiplied by 2, you get 55. Okay, and 55 is the frequency for the note A1, which is 1 octave above A0. Okay, it has double the frequency. the frequency of 27.5 multiplied by 2 is 55, and so on and so forth. And let's look at the next portion of the table. Okay. Next portion of the table. You see the discrepancy between the piano key number, right, and the power here. Right? For example, if the piano key number is 13, the power is here is 12. That's why you have n minus 1. Right? 13 minus 1 is 12. Okay, so that's based on the formula for the 12-tone equal temperament. Okay, so now let's look at one more octave, and that one I give here, starting from the note A4 or A440 at exactly 440 Hertz. This is when the frequency that the whole concert is tuned after. So you see that after 12 semitone, you see the frequency of A5 is exactly 2 times 440, right? That's 880. Okay, so here the factor is 32. So that means that if you take 27.5 multiplied by 32, you get 880 Hertz. Okay, or up there 27.5 multiplied by 16, that's 440 Hertz. All right. This frequency factor here. So that's the meaning. So therefore, the construction of this spreadsheet should be clear by now. It's really not so difficult. The first column is easy. You can go through using the formulas for all the columns, except that just for this column here, I ask you to create your formula just by using if then else, right? Okay, and you have the solution guide as well. Be careful. And look at the report. You need to be careful. There are imperfections. Okay, so some teams did very well. Problem 4.7. Some of the teams may not be up to standard. But this is the solution here. This partial solution, if you like. So your spreadsheet, you want to look exactly similar. Okay, very simple. So any questions on this? Yes, Marcia.
We're explaining what you spreadsheet should we include like what you were saying about like the C lines first, or should we just explain the
Could you repeat the question?
When we're kind of explaining after you show the spreadsheet, should we explain the music or just like
Yeah, if you know, great. Yes, if you know, great. Otherwise, my only request would be to create the spreadsheet. But if you, so for example, what would you like to explain? No, yeah. So the minimum, all I'm asking is just to create a spreadsheet. I'm not asking anything about the music theory. I know many students in the class do not know music theory or cannot read musical score from the informal poll last time. Yeah, so I'd like to create. For this version, for the version of this semester, I toned down on the music theory. And last semester, in the fall 2014, I did rather extensively on the music theory, and it's recorded on video. So therefore, anyone who is interested, I would like to invite you to watch the video of my lectures last semester. I will mention more how I lighten up the music theory. Okay. So with this, I now move on to motivate this section. This topic here. Okay, and this is the second motivation of real-world problem. Okay, the first motivation of real world problem is through earthquakes, and that's how you need to use fast Fourier transform, which is an advanced level of Fourier analysis. And so here the second real world application of fast Fourier transform is through this music note detection, okay, of the Beatles song called A Hard Day's Night. Now, there's a song and the movie. Both the song and the movie are classics. Okay, the movie is ranked number 5 as the best movie of all times on the Rotten Tomatoes website, which is an aggregation of the reviews of movies. So we'll come to that. But let me show you the goal, okay? My goal is this paper here. And let me zoom in. Okay, you see, you look at the title. The title is Mathematics, Physics, and a Hard Day's Night. Okay, with the word mathematics first, second is physics, and only the Beatles the third. All right, and so, and clearly this is. I just discovered something. If I use the down arrow, I zoom out. So I'd like to explain to you so that you can share the enjoyment to explain to you enough so you understand this paper. And let me show you the goal. Okay. Yeah, we can do that. But let me probably introduce to you. Okay, what is it? Exciting about this story. So let's look at the movie. And so what you want to perhaps maybe let me bring up section C here. Right, I have it here, and I just zoom out so you see where I'm navigating. Okay, right here, perhaps. This is an article, and this is the opening chord here. Check. So when you listen to the song, pay attention to the opening chord, and this is the most famous chord of all rock and roll. Right? This is by the Rolling Stones, 2001. Quirky, arresting, unmistakably original, the musical equivalent of the song's title, the music and artistry of the Beatles. A hijacked church bell announcing the party of the year. Guitarist, magazine 2000. The opening chord pretty much defined the sound of an era, rock and roll, that is. Guitarist 2000. The opening chord of the song was like an amazing wake-up call. Okay, so I have here a YouTube video, and I just want to show the beginning, okay, and then we'll look at the rest later. This is just 2 minutes, but only the beginning. And let me try here. I need to turn on the sound a little more. Just pay attention to the first opening chord, okay. Yeah, so that opening chord is the goal of the real world exercise here. And so let me provide a background for those of you who are not familiar with this story. Okay, so the song and the movie was released in 1964, and so until last year, that was exactly 50 years since its release. And it's famous and mysterious because the first chord was not written in the musical score, so that many musicians tried to replicate the first chord and then came up with many different versions. Okay, And even when I check the web, last semester when I taught this, when I prepared my lecture notes and taught this topic, there was still discussion about how to play the first chord. Okay, as fresh as October 2014. The song's asymmetrical opening chord, asymmetrical means it's not following any rule of classical music. Non-metric, opening chord is the most beguiling in the band's history. People have been trying to figure it out and or reproduce it for 49 years, and because this article was written in 2013, so 49 years since 1964. Okay, and so this is I just showed you this page, and this is a very nice black and white photo on the DVD, on the CD of the song. And this is another. This is at the cover, and you see that. I mean, this fellow here is clearly not Paul McCartney. So somebody inserted his photo into this image that I got from somewhere in the web. But the point here is, okay, there's some quotation. This is George Martin. This is the Beatles producer. He said, "We knew it would open." It means the song, right? And the opening chord would open both the film and the soundtrack LP. So you heard the opening chord at the beginning of the film, right? So we wanted a particularly strong and effective beginning. The strident guitar chord was the perfect launch. So, and this is from the paper by Jason Brown, a professor in math, who used FFT in 2004. So that's 40 years since the release of the song. Okay, and he used FFT to detect the note in the opening chord. So he wrote, many a guitarist, whether professional or amateur, has tried to reproduce the chord, but the voicing of the chord has remained a subject of much discussion over the past 40 years. In fact, can now be corrected as over the past 50 years. Because I told you I was looking on the web last semester, and I still see debates about how to play the opening chord. Okay, and so this is another quotation here. 50 years after its original release, the film still holds and ranks as a classic for all rock and roll movie lovers. This is a photo in the movie. Maybe to zoom out here is better. And this is a screenshot that I took from the site, the Rotten Tomatoes, and it was ranked 7 as of September 2014. But when I check it again in October 2014, same year, just or about a month later, it jumped up to rank number 5. And I just checked before I come to class, it's still ranked number 5. Okay, so as the best movies of all time. And I'm sure if I zoom out here, I'm sure everyone heard of The Wizard of Oz, The Godfather. If you are a movie buff, you may have seen Citizen Kane, a famous movie, Modern Times of Charlie Chaplin, Singing in the Rain, right? So all these, I'm sure you probably have heard of. But, oops, zoom out. Oops, sorry. Yeah, what I wanted to point out is you can see, for example, E.T. Extraterrestrial, right, number 16, and A Hard Day's Night is number 5. Okay, now, Toy Story, yeah, so all of these are probably popular and well known. Okay, and this is a screenshot from the Rotten Tomato. You see with the tomato meter, 99%, and this is rating from the audience. This is probably rating from the movie critics here. Okay, and related to the paper by Jason Brown, there are many theories, meaning versions of how to play the first chord, and Jason Brown listed 3 different transcriptions or versions of the first chord that he found on the internet before he used fast Fourier transform to come up with his own version, and scientifically and mathematically based on fast Fourier transform. Okay, and there are more transcriptions than the 3 that were listed by Jason Brown. And so that's the goal. The goal is I'd like to give you a real-world experience of using fast Fourier transform. Okay, and let me. I have prepared a list of topics covered here that I pointed out some of the features right here. Okay, what does it mean real world? Real world is complex, long, challenging, messy. It's not small problems with solutions from the instructor's manual, like statics, dynamics, mechanics, material. Okay, long, messy, challenging. Not having sufficient input data. Real world problems, sometimes you don't have enough input data. In a typical problem that has a solution in the instructor's manual, you have all the numbers that all you need is to put all of these numbers in the problem statement in the solution, and things work out, right? Sometimes in the real world problem, you don't have enough data, or you have more data than necessary, and you need to select which part of the data you need to use. And you need to bring knowledge from different areas together. And in this particular problem, you need to know the physics of musical instrument, the piano, the guitar. And that's what Jason Brown did, by the way. He was the one who had, not just that he was a mathematician, but he was also probably a guitar player. And so he knew about the piano, he knew about the guitar, and using all of this knowledge, and like I said, sometimes you have too much output data. Well, so here in this case, output, okay, above here you don't have enough input data, and here you have too much output data. What does it mean, output data? That's the fast Fourier transform spectrum. You have a wide range of frequencies and a lot of peaks. How do you eliminate things that are not essential in order to glean out the essential, right? So may have too much output data, need to select relevant output data for your analysis. And you may have more than one solution, not just a unique solution like typical small problem in the textbook with instructor's manual solution. You usually have only a single answer, but here you may have multiple answers that can be valid. And let me explain. Sometimes there's a concept in music called the octave equivalent. If I have time, I'll explain that, but I do have the video from my last semesters. The octave equivalent means the following. You remember the octave? You have A0, A1, A2, A3. When you play these sounds, when you play these notes together, they are called consonant, meaning they sound nice together. So the ears can pick up, even if you miss certain notes, the ears can fill in the gap for some reason, and it's called psychoacoustic. Okay, that's why last semester I showed a song, Happy Birthday, everyone knows that song, and they purposefully move certain notes up or down by one octave. And when you listen to the song, even though the notes are completely not exactly as scored, in the music sheet, but you can still detect the song. Okay, so that's what it means by having more than one solution. Because the ear is a very complex computer. It has a way to compute the sound and detect the sound. Okay, and right now we still don't understand how the ear perceives the sound, and the perception of the sound is part of a field called psychoacoustic. Okay, we don't get into that. Okay, so here I just really want to show to you. I hope that this is fun. Yeah, thank you, Casey. That you combines math, physics, engineering, and rock and roll. It's I hope less boring than the usual topic, and this is the underlying reference. Okay, and time is running out, as Casey pointed to me, and so I'd like to show to you only one thing, and I hope that it's short, and I hope that that would motivate you even more. Excuse me, let me search, and this is I'm going to present my method at a conference of the American Society of Engineering Education in April, just a few weeks from now. And I have here, okay, a slide that I just want to show to you. Only one slide. Okay, and that's this slide here. You remember that I asked you to fill in the survey form, right? Most of you answer that you took this course because it's required. A few, say that because because you are interested, but most answer that because it's required. As you saw there from last semester, 80% of the respondent, not so different. This semester 75, but most say that you took this course because it's required. And then after the Beatles topic, I also surveyed the class, and this is the result. You see, this is like anemic, it's one-sided. Most people are not interested, but here, look at this. After the Beatles topic, I asked, did the Beatles topic help increase your interest, regardless of your initial attitude regarding the course? You see, this is more like a real world here, and you see 4 and 5, this is very interesting. So these students, 4 and 5 represents 42% of the respondents, show that their interest had increased because of the Beatles topic. Now, there's still some who were turned off, and this is because of the music theory. That's why in this version here, I try to tone down the music theory. I just want to teach enough so that you understand and enjoy the paper by Jason Brown. For those of you who are interested in the music theory, I invite you to watch my videos of my lectures last semester, okay, in which I get deeper into the music theory. So with that, please, lecture summary.
Because every time I hear it, the key explodes. That would be a good practical joke. Replace everyone's C4 key with actual C4. Might kill someone. Well, actually, you definitely would. Probably. Almost positive. As long as there's someone there to press the button. Good music.
Yeah, I'm gonna.